Actually, one of the joys of it is how useful the amateurs are.
Yes.
The
Yes, I
professional
think
astronomers actually are, making these seminars and things because they can't cover the sky as well.
and there's a whole history behind that. I don't want to get into it tonight, but the whole existence of AAVSO is because of Pickering's desire to have amateurs participate. So it's not a new thought.
They talk about that in Glass Ceiling, but it sure sounds like a Astro Cafe talk, David.
Oh yeah, for sure. Yeah, I've gotten a lot of out of AAVSO. I have to admit, for the amount of money I've spent, like on the membership and some of the courses, I've just an immense amount of stuff came out of it.
Oh, you have to pay to get it to.
Well, you don't have
to volunteer for them, eh?
No, I belong to them because I get a discount on the courses. I pay like basically half price, so it's a good deal.
And then there's an organization that does spectrographs called ASAM or something.
I don't know of that one, but AAVSO has an umbrella, like it does exoplanets as well. So they have quite a number of things. I mean, anything that would cause a star to vary, they kind of do.
Mm-hmm. Well, I think it adds a lot to the experience. I'm all in for the stamp collecting, seeing the different things. But when you add the photometry and spectroscopy and all the other wonderful aspects of astronomy.
Well, to me, it just kind of enriches it. Like before photometry, I had a two-dimensional view of the sky, and now I have a three-dimensional view.
Yeah,
of the sky.
yeah.
That time domain really adds a lot.
Randy, I started my diet today.
Sorry.
So I don't appreciate that.
You get to stare at a pie the whole night.
Yes, it looks like a nice pie too. Sorry.
So that's the diet.
There's a lot of fruit in it. That's pretty good.
Yeah, and the image, the image is locale.
Oh, yeah. Where?
This is the new moon called the blueberry moon.
Yeah. And
Oh,
then
there you go.
there are all those,
Dave. There you go.
all those cookies from Diane's celebration.
Nicely done. Did you make that, Randy?
No.
Oh,
No.
who did?
Sorry.
Okay. So Nathan, I see you're a published author.
Oh yeah, I got another article published, which I was pretty excited about.
Good for you there, buddy.
Tell us about it. What was it?
Well, people were interested in how I took pictures of planets through my telescope.
Recording in progress.
It's in there in Sky News. Excellent.
You
Go ahead.
Okay. Now that the feedback loop is closed, people wanted to know more about how I took pictures of planets through my telescope, because I think last article I had just shown the Venus sequence, but this time I got to show all my planet pictures too, including the one of Earth. I tried to maybe increase some of the resolution, but it's not. It's just a dot. Anyway. And then I also started getting my cartoon series, Nerd Anomaly, published. It's kind of small, but it's there, which I'm excited about.
There you go.
And if you look at Margie's screen there, yeah, you can see.
Yeah, there you go. Yeah.
And does everybody know to watch Nerd Anomaly on Instagram? Because they're coming fast and furious and they're really good.
Good for you, Nathan. So Nathan, how do you think of these things? Like, I like your curiosity killed the cat thing, but that's good thinking.
I mean, I'm a self-proclaimed, actually, no, not self-proclaimed. I've been proclaimed by many as a pun master. In grade 8, I took over bad pun of the week, which the grade above me had set up, and I turned it into bad pun of the day. And then by the end of the year, it had become bad pun of the hour.
Uh-oh.
And on the last day of school, there was no room for anything else on the whiteboard because it was just totally filled with puns. I recruited a few of the grade 7s who are now grade 8s to take over it. And I warned them of what would happen if I came back and it wasn't there. I'm just kidding. I didn't do that. But anyway, so then I decided I had already made some like sketches in some of my school books of like, they were just stick figure cartoons, but I decided that I could actually make something out of them. So I started a cartoon series.
Good for you. You've become an influencer.
Thank you.
You remind me of a guy in our engineering class who did cartoon caricatures of all the professors we had.
Be careful.
You're right. I guess
Careful,
it better
right?
be. I already have like a cartoon of, I could imagine a cartoon of my high school teachers. So
Yeah,
Randy,
watch out for the Astro Cafe
Yeah.
cartoon characters based on this,
I
on
know,
the
but
faces in the Hollywood squares here.
Yeah, right.
Randy, I'm looking at your background there. It's a moon pie. I like that.
It's really good, isn't
That's awesome. I bet it was good too.
it? Somebody
Should
named
become
Rachel
a-
Leung made it.
I
Yeah,
better be
confession
careful.
time, Randy didn't actually get to try that one.
Oh,
it probably reached its quarter phase quickly.
Good one, Nathan. No, my goodness me.
He comes by that honestly, doesn't he?
My goodness me. Why didn't I think of that? Very good.
We'll just wait another couple of moments to see who else is coming along this evening. Just as a heads up, and if Margie, if you're ready, I will call upon you first. So just so you know.
Brian, Barbara, it looks like you're outside.
Well, no, that's just another background from the picture Mount Tomei. And maybe I'll head there later tonight though to catch the first quarter sketch opportunity.
Give it back. And it's open.
Yeah, it looks like we're expecting a bit of a decline in weather for the next few days. So tonight may be a good night to get out.
Mhm.
Yeah, it's not a good time for the weather to turn bad. I have homework to do for my photometry course.
You may be delayed.
I can do the darks and the biases
There you go.
and the flats.
Just to go over who I have on the list tonight for speakers. So we have Margie, then we have David and Randy, I think are doing a related topic. Then we have Nathan and Bryan with photographs, Dave Payne with a book recommendation. John, I don't see here yet. He had something he wanted to share, and we have 3 Edmonton photos. So it looks like a pretty full evening. But we'll just give it another, I just see a few more people who just arrived, so we'll just give it another minute or two. Oh, and Randy asked to remind those of you who are on the council that we're having a meeting tomorrow night in this same place via Zoom. So 7:30 for those who are on council.
Hey, Chris, no photos to share tonight. That could have been an email from a couple of weeks ago.
Oh, okay.
We will be talking tomorrow about the future of Astro Cafe under COVID. And so if anybody could give some feedback, as you can tell, we're not doing hybrid.
An irrational
at
link.
least not yet. But do contact either Chris or me with hopes and dreams and thoughts.
Donuts would be good.
Virtual donuts.
No,
You're on
no,
a diet,
real-
you said.
Real donuts.
Better.
You can have real donuts, just get them delivered.
Yeah,
Everything's delivered these days.
yeah, you're right.
Yeah, we had a meeting at work while I was still working, and they did they had the cookie guy come around. I think that's what he's actually called, the cookie guy. Drives around in his smart car and delivered warm cookies to meeting participants just in time. So that was quite fun.
Hmm.
Did you get to pick the type of cookie?
No, they were, I don't think there's too many choices, but it was chocolate chip. They were good.
Yeah, it's
They
guys
weren't
like that. Guys like that that are driving the COVID 10 pounds that we're all probably guilty of.
Indeed.
Yeah.
Great. Well, maybe we'll get started. So as it's a little bit after the start time. So welcome everybody to Astro Cafe, the first one for September. As has been mentioned, Randy was saying just a few moments ago, we had hoped to start a hybrid of both in-person and Zoom meetings, but that's on hold at the moment due to and with the newest requirements today, we'd actually have to check your vaccine status. And I guess to attend a non-essential event like Astro Cafe, you'd have to have had at least one vaccination and would have to be prepared to prove it. So that would be yet another step in the hurdle, including things like seating plans and I guess knowing who was there and no food and things like that. So I think we're better off at the moment staying at home where we can have whatever food or beverage we want, and we're not at risk at home. So, but if you do have feedback for us, and we do, it is our intent to, as soon as possible, return to having these having some in-person component as well. But it's got to be manageable for us. Right now, it would just be too much. Anyways, so the speakers I have this evening, I'll just say that again. So we've got Marjie, David Lee and Randy, Nathan and Bryan, Dave Payne, John I don't see yet this evening, and some Edmonton photos from Dave. And is that Bryan, did you say yes, you have photos? Sorry, or no, you don't. Yeah, that's what I thought. I hadn't put you down there. And I'd just like to say welcome to Wendy, who is a new member, I believe. And so welcome.
Thank you.
And hope you enjoy. It's a fairly informal group, and we're not quite as crazy as we seem, I guess. But
oh, I hope you are.
Oh, good. Okay, well, that's maybe good. Anyway, so with no further ado, then let's Marjie, are you ready to take it away?
I am. Okay. On Saturday night, I gave a presentation about women in the history of women, a very short and brief history of women in astronomy. And so I've read a list of women, of Canadian women who were and are astronomers. And this was one of them. As I looked at what all of these Canadian women have accomplished, I must admit I was just blown away. So here is one, Dr. Tanya Harrison. She describes herself as a professional Martian. She is a Canadian. She's about 37 years of age. I found it very hard to find how old she was and where she was born. She lives in Washington, D.C. and in Toronto. She is a planetary scientist and manager of the Federal Science Program for Earth Observing Satellite Company, Planet Labs in San Francisco. At age 5, she watched Big Bird in Japan and became interested in space. Big Bird in Japan is about a princess who lives on the moon and comes to Earth and then goes back to the moon. She has a BA in astronomy and physics from the University of Washington. She has an MA in earth and environmental sciences, a PhD from the University of Western Ontario Centre for Planetary Science and Space Exploration. She worked with commercial space company Blue Origin. She was on the NASA science team of the, let's make that Mars rovers, Perseverance, Opportunity, and Curiosity. She is a fellow of UBC Outer Space Institute, which is a group of people who are experts and they are focused on the sustainable development of space. She is a respected Mars expert whose specialty is geomorphology. She researches in Martian geomorphology and terrestrial analogs, spectroscopy, and glaciology. She's done work on gullies on Devon Island in the Arctic as an analog for Martian gullies. And apparently Martian gullies are a very complex formation system. She has received 2 NASA awards, the Amelia Earhart Fellowship, Vanier Canada. She received a Vanier Canada Grad Scholarship, she was one of VIA Satellite's Young People to Watch in 2018 and a Future Space Leader in 2019. She does TV documentaries, interviews, she writes, she's the speaker, she mentors other people. She's an educator, a community, she's engaged in community engagement with focusing on initiatives for diversity, inclusion, and accessibility. I also looked at a couple of websites she has, and she designs logos for t-shirts that have to do with space. And she is a professional photographer.
Got all.
What does she do in her spare time?
I'm trying to find the stop share, but I can't. I can't.
She spoke to us and was quite involved. And I think it was the 2018 General Assembly in Calgary.
Yeah.
Quite a few of us met her there.
Yes, that's where I remember her from. Yeah, yeah, for sure.
Neat.
That's excellent, Margie. Excellent.
Thank you.
Yeah, and she's only one. There are so many more.
Mhm.
You're going to give us more of these?
Pardon me?
Will you give us more of these presentations?
I was thinking that I would do that.
Mhm.
Great.
Yeah, very good, Margie. You know what? What's a problem with Canadians? We're way too modest. It turns out when I worked at the NRC up on the Hill, I was always whining at the director that we just simply don't blow our own horn. And he agreed. He says, that's very Canadian, big deal. So the one that really stands out to me, and I don't want to steal your thunder at all, Margie, but I'd like you to continue this. But the one that really stands out to me is the first planet that was ever directly photographed by an astronomer was done by a Canadian, one of our guys up on the Hill. And guess what? Astronomy Picture of the Day said, oh, you're not really the first, because they went back through all their archives and picked out one photograph that happened to show the planet now that they knew where it was. Said, no, we were really the first, not you Canadians. So I was a bit pissed about that. And I told the director that too. And he said, well, we're very Canadian. So I really applaud you for bringing forth Canadian people who are amazing like this, because we just simply don't hear about them. That's all there is to it.
I think the problem was, as I recall, that picture was unveiled at the Moon Underwater Pub at a Christmas get-together.
That's all right. Yeah.
I'm sure some of you were there. I know some of you were there.
Well, I think you're talking about the one where like the A, B, and C that was kind of going around. Is that right, Gary?
I think so, yeah.
Yeah. Actually, I think the first time it was ever done was when there was a Canadian stamp. And we were all up at the DAO, and it was a Canadian stamp that was being like unveiled, and he showed that up there. I remember that. Now I don't know whether that was maybe the first time, but it certainly was part of that. Was anybody else there? Years ago now.
Yeah, it's quite a few years ago.
Yeah.
So keep them coming, Margie.
Yeah.
Will do.
Yes, thank you very much. David Lee, are you ready to roll?
I guess so. Randy, did you
Or do
want to
Randy
do
want
it
to go
after mine, or?
Oh yeah, you go first, sure.
All right.
Whichever order you guys want to.
Okay, so this is a story that kind of begins at the beginning of this year. But what you see tonight will be more about, I guess, my journey or my experiment in exploring variable stars. So at the beginning of the year, I decided I wanted to do something different in astronomy. So I thought I was looking for kind of things to do. And originally, I didn't go far off the map. I was thinking I was going to do variable star observing with my CCD camera. So that's where I started. So I joined the AAVSO, and that's an American organization that studies variable stars. And I got a mentor, and we started kind of working about what kind of equipment I would need and what kind of skills I would need as well. But sometime during the summer, I'm not sure what got into me, but I thought that maybe I should slow down a little bit and do some visual variable star observing. And I did take a course, and I also had produced a list of things to observe. And I'm sure glad I did. So tonight is a little piece of that. So after having completed that course, RS Ophiuchus had an outburst, and I'll explain what that is in a second. But that happened really early in August. So I spent, whatever clear sky time I had to observe it. Now, was I successful? Partially, but I don't want to ruin the story. So what is RS Ophiuchus? I'll explain what that is. And how did I find it? Through star hopping, kind of an ancient practice now for people that have go-tos. And how did I use visual differential photometry? So those are the three elements. And what is it? So variable stars are any kind of star that will vary in terms of its brightness. And there could be lots of reasons for it. They actually split it up into two branches of variable stars, intrinsic and extrinsic. So the intrinsic ones are ones that actually vary in brightness because of things that are happening to themselves internally. And this is a case of an intrinsic. And in fact, it's called a cataclysmic as well. The extrinsic ones are to do with things that are eclipsing. So maybe there's a binary pair and one is going over another one, sort of like an exoplanet, and actually reducing the brightness. So there are way more examples of that than I can even name. There's probably hundreds of different types of variables, and brightness changes for various reasons. But in this particular case, RS Ophiuchus is actually quite famous, actually. And it's called a recurrent nova. So what that means is it doesn't destroy itself, but every once in a while it gathers fuel and flashes. So I'll explain that in a second here. So there's a white dwarf, a red giant typically. And these may have started off as being a pair of stars that had sort of orbits around each other. But eventually all stars, I guess just like people, all stars start to fade. And the white dwarf usually comes about because it loses fuel. And when it loses fuel, it becomes extremely dense. It will sort of collapse on itself and become small, but extremely dense. And its companion, which is nearby, will often be like a red giant. And it will occasionally steal fuel from the red giant. And it envelops itself in fuel, kind of like almost like lighter fluid. And then when it builds up enough fuel, it will actually ignite. It'll actually produce this thermonuclear explosion. So RSFU is something that experienced a recent outburst. So that happened at the beginning of August. But it has a full history. You can see that it has a range between 4.3 to 12.5. Now, just to give people an idea, the Dipper stars are, I think, like 2.3, 2.4. So bright stars that we can see in the city are even brighter than this. But having a magnitude of 4.3 is quite phenomenal for this. And you can see the range. It goes in its quiescent stage as dim as 12.5. So it is very unusual to see it at its outburst. So you can see the records of outbursts. They're typically every 15 years. I don't know how exacting that is in terms of these outbursts. None of these are terribly exacting. They're just approximately every 15 years. And the 1907 and 1945 have no actual observations. Now, I'm assuming it was because of wartime. I'm not quite sure. But they're probably inferred from the archival data. It was likely there were outbursts at that time.
It's from the, they were behind the sun.
Oh, is that why? Oh, I didn't
Yeah.
really know why. Well, thank you for confirming that. So the first thing I did, being an AAVSO member, and by the way, people don't have to be an AAVSO member to use all these tools. There are some features of the tools that are not available to you unless you are a member, but the majority of the charting and things are available to you, even if you're not a member. So the first thing I did was I used the variable star plotter, and this is quite useful. You just type in the name of the object. So I just typed in RSOPH. Now, the bigger challenge is knowing how to label these. I think Margie asked me once what these letters mean, but there's a whole naming scheme in variable stars where they start off with sometimes just with the name itself. If it has like a Bayer designation, they'll just start off that way. And then when they want to differentiate them, they start going through the letters of the alphabet. So this one has gone quite deep. This is already to 2 levels of letters in the alphabet, but they go even beyond that. But I won't go through all the things. If you want to look it up, you can find out the algorithm that they actually use. So you end up with a finder chart like this. And a lot of people wonder about what these numbers are as well. And I'll just briefly explain what those are. The target star is actually identified by a crosshair. And then you'll see all these stars of numbers beside them. And they look kind of odd because you think, well, they can't be magnitudes, right? Because they're values like 83 and 54, 78. So it's historical. These charts are actually showing the magnitudes without the decimal place. And the reason why they do that is they don't want you to mistake the decimal point for a star. So they just use the numbers. So these numbers that are here for a purpose. They're actually part of something called a sequence. And these stars are devised for this particular target for a specific reason. And the reason is it's to allow you to do differential photometry, which I'll tell you about in some future slides. So basically, these are the comparison stars. These are the stars that we're going to compare the target to in order to determine what this magnitude is. So in other words, there's no computers involved. There's no photography involved. This is the human eye differentiating brightness. So you got to find it first. So I resurrected my visual observing skills and used something called star hopping. Now, those of you who grew up on go-tos and never did this, this may not be familiar to you. But for those people that resisted go-tos, this will be very familiar to you. So what we do is, especially if you're still using star charts as opposed to kind of digital versions, digital planetariums. It wasn't uncommon for people to sort of create little wire rings that show a particular field of view of an eyepiece, let's say. So I'm just indicating how this might be done. And I think in Sky and Telescope, there were articles where people actually took wire, like copper wire, and actually formed them into a field of view that was consistent with a particular eyepiece. Now, I chose to go really primitive for this visual observing. I went with my small binoculars, and my small binoculars are approximately 6 degrees field of view. So I basically created a field of view for myself inside. Now, I didn't use a physical star map. I used the Sky X, and I created a field of view which was consistent with that. So the idea behind star hopping is that you look for sort of major mileposts, like here's Altair and here's Vega. So when I looked up into the sky, and this is southwest, I was looking for Ophiuchus. And Ophiuchus is this kind of odd kind of pointy shape, kind of like the point of a pen or something like that. And it's quite broad, it's quite wide. I basically kind of started at the top because Razorhead is actually quite bright. So I started there, and you can see that I sort of created this kind of linked path of fields of view. Now, I didn't literally do this with binoculars. I just looked at the path, and I knew I would be starting off here. I just keep slowly panning down until I hit this series of stars down here. And then I would travel along here and then travel up. So at that point, I got into the general area, and this is where the finder chart comes into play. So you start with the easy milestone, you navigate, and then you switch to the finder chart. So here's the finder chart again. Now, the first thing you have to do with the finder chart is build these asterisms in your brain. So I kind of looked at this, and I could see that there were 2 stars that were vertically, or I could probably draw a line through them from where the target was supposed to be. And there was a triangular pad of stars as well. Now, what you don't see is the 2 stars that I used on the side, which are not in this field of view. As I was coming up around Ophiuchus, there are a pair of stars. And then if you come across, you'll see this, and you'll see where the target is supposed to be. So now you see these numbers here, 4.6, 5.4, 5.9. Now, when the outburst started, I think it was started at like 4.8. So I knew I would be wanting to compare to these stars up here. So these are the same ones here. So I used 4.6 and 5.4 early in the outburst. And then I used 6.9 for nearby star as well. So as I mentioned, I used 8x42 binoculars, 6-degree field of view. And bear in mind that the limiting magnitude is 8 to 9 for this at its best. And I'm also living in a suburb, so it kind of limits me. But anyways, I started this way just to gain the experience of doing this. So here are my results. Now, the differential photometry basically is predicated on taking your target and then comparing it to stars that are nearby. And the sequence is actually devised by the AAVSO. So these are known stars. We know they're not variables. We know they have a constant magnitude. So they are used for comparison. And typically what you would do is you would bracket, you would look around the field. And in fact, I had to make some quick decisions when I was out observing, because I had to find things that were close to the target. Now, it was very obvious during the first outburst, it was extremely obvious. I came up with an estimate of 5, and I think the literal curve showed 4.6. So it was close, it was within a margin. None of these things are terribly exacting. In visual observation of variable stars, you could be out by up to a magnitude actually. So this is quite good actually. Also, we also note the conditions, because these are much of a factor in determining how good your observations are. I didn't have very good observations for any of these actually, in actual fact. There was quite a haze. I think there was still a lot of haze from smoke from forest fires. And then the next time I could see it was like a week or so later, and there was a slight haze as well. And I question some of these values here now because, using these notes and understanding that there's actually a common error, I think I may have mistaken the target, another star for the target, which probably would indicate why my estimates didn't really vary very much when you can see them varying in the actual light curve. So I've got time to go. I haven't reached 12.5 yet, and it will be. It's actually slowing down apparently, as it normally does. It's quite a rapid descent, and then it slows down. So here's the light curve. So on September the 12th, this would have been yesterday. This is a sensor-based reading, not a visual reading. It shows us at 9.4. Now, if there were some visual readings here in the light curve, we would have seen some variance here. I mean, we could have seen it as bright as 8, perhaps, and maybe even a little dimmer. It really depends. So at this point, I really need to go to a bigger telescope, or I'm going to have to start using the sensor to do the rest. So here's the curve now. You can see at the beginning of August, it had a huge spike and then started to taper off. So these numbers down here are Julian dates. A Julian date is basically a date with a moment in time as well. So these numbers actually encapsulate an exact moment in time. So this is like a time series, and these are the brightness levels, the magnitudes that are estimated either using digital photometry or using visual photometry. So I don't know if there's any questions. I'm going to leave you with some reading material. I'm going to throw these into the chat, and yeah, enjoy. I really encourage everybody to try this. It's actually quite simple, and I'd be more than happy to maybe open up a few workshops just to describe the process again. So over to you, Randy.
No
David, can I
questions?
just
Oh, yes.
I just ask
Yes.
what are the different colors and at the different brightnesses?
Yes. So I believe, I don't have my legend with me.
Oh,
but
one
I-
slide before. There it is. Nope.
Yeah.
There. You've got
Oh,
the
yeah, right
legend
up
up
at
there.
Yeah, that's the one.
There you go. There you go.
It's
Yeah.
up there. Oh, okay.
Yeah. Yeah, I just closed in on it to show you the actual curve because it was obscured by the tag. But yeah, there's varying things. These are actually filters. One thing I didn't describe in photometry is it's not used in visual photometry, but in sensor-based photometry, the way to make all the readings usable. And what I mean by usable is, this is the law of averages. Like this database is populated by numerous people around the world observing it with different cameras. And the only way to make the readings comparable is to use filters of specific wavelengths. So these are, I don't know if you've heard much about narrowband filters that we use sometimes for imaging some of the beautiful photographs that we see in the club. But these are very specific wavelength filters that are used for photometry. And it just means that only certain wavelengths of the stars come through, and that actually makes it consistent. So through calibration and using these photometric filters, you can actually compare one person's work to another person's work as long as they're using the same bandpass filter. That's what those things are.
And down at the bottom, it says there's 70,845
Yes.
total observations that people
correct.
have taken.
That's correct.
Okay.
But don't forget, the AAVSO has been around for a long time now. I think non-visual observations have only been taking place for the last 20 years. I think. I keep forgetting. I mean, there's photographic glass plates, but in between, I keep forgetting this. There were photo multiplier tubes as well. They're kind of a precursor to CCD cameras, and they were used for capturing light values as well. Yeah, there's a whole history of photometry actually.
So David, the couple of guys in Edmonton were doing the same thing as you with binoculars. And I've got a note from Alistair Ling that I received that he said he was looking at it 7x50 binos from his backyard. He said the Mag 6.3 comparison star was easy, but no sight of the nova. He double checked the 6.9 stars and could see them no problem. So he waited 5 minutes and then could just barely see the nova.
It's very difficult to do.
And he said he pegged it at 7.1, and that's the 17th of August. So it would fit in with what you saw the couple of days later.
Yeah, there's a lot of variation, and you do have to bear that in mind. And I don't show this as an example of perfect visual photometry. I really show this as a person just starting out practicing.
So do you mount the binoculars?
No.
So
no,
I wanted to see myself getting totally frustrated.
I wanted to challenge myself, which I did. But I did allow myself the courtesy of having a chair. So I sat at the end of my driveway and I star hopped. I scanned with the binos. I mean, this is so not like me in a way. Like I would have just preferred to have just pushed in the coordinates and got there. But this is a different experience. And I was saying to Sid when I was doing this that, you know, I had forgotten how constellations twist in shape as things rotate, and it's not anything I would notice, right? Because if you're plugging things in, you don't see that, right? But here I am, I'm forced to watch and observe the night sky in motion, right? Which is quite a different experience. Very different experience. I really encourage everybody to do it. Even if you have a go-to, you should try this.
And your glasses weren't an issue?
No.
Yeah, for my visual observing when I'm doing star hopping, because I don't have any setting circles, anything on my telescope, I did the same thing. I printed out on transparent paper the field of view of a variety of eyepieces for my telescope, and I just lay them over the star charts.
Yeah, you could do that as well. I mean, I've known people that take a literal chart, and remember I said that people make these kind of wire frames, right? And they'll just move them along and look for the next piece. And they just have enough overlap, like based on the field of view, you just have enough overlap to get there. But, you know, to me, I just kind of memorized the motion. Like it was like a J motion. I knew I could start at the top. I would scan down. I could do it relatively quickly, looking for the features. And then I would sweep down. Then I found the horizontal band of stars in Ophiuchus. And I swept on my way up. And I'll tell you, it's very hard to attend to the detail that will tell you that you're in the right place. Like you can get really close, but you know, like a little bit of haze threw me off, and I'm pretty sure I picked a different star. I didn't.
Yeah, when you're pushing that magnitude, it's really hard.
Yeah,
I was able using those little setting circles and your anometry. I was able in my 8-inch telescope to find some 13.1 magnitude galaxies in Leo.
So are you memorizing the star chart before you're going to it? Or are you referring back and forth? Because that's the hard part.
I study it beforehand.
Yeah.
So I look at and I anticipate what I'm going to do. So I do have a couple of strategies. They don't always pan out because I'll look and I thought, oh, that's way dimmer than I thought. Oh, the other thing is I really learned about magnitudes with my instruments now. Whereas before, I probably couldn't have told you like what mag something was. Now I really know. I intimately know because I can either see or not see them now, right?
Yeah.
So, and then the other thing was noticing variation in the sky. I was never very good at that. I can pretty well do it now because I had to look, right? Like I wasn't pointing using another device, right? Lots of value in doing it.
Yeah.
So David, I was intrigued by your explanation of the matter from the red giant falling onto the white dwarf like a layer of lighter fluid.
I just made that up, but
I mean, okay, because
well,
I was having a hard time understanding how that might.
We'll be talking about this.
I think, yeah, Randy will probably talk about this, but it's basically accumulates fuel, and maybe Randy will answer your question.
Okay, great.
Yeah.
David, what's the precision of your visual magnitude estimates?
Okay, I don't know if I'm this good, but I've been told that people can get down to a 1/10 of a magnitude. I find that hard to believe. But then again, the standard deviation is ±1. So maybe that's all right.
Well, I think I was going to say, if you have known standards nearby, that must improve your accuracy. And I'm sure that's the whole point of practicing this, right? You do it over and over and over again.
It does. And, it's not that hard, like that triangle of stars. I looked at it and I looked back at the target and I looked back at the target and I thought, okay, here's 2 comparison stars and they bracket where this star is. So I just started looking at them. There's 2 methods, apparently. There's the Pogson method and the fractional method. I can't describe the Pogson method to you, but the fractional method basically is you take 2 values and you think about how far along it is in either direction, like a halfway across, a quarter of the way across. So you use that kind of fractional estimation to get to where you need to go.
David, I have a question about whether or not you had to use averted vision to actually see it.
I just kept looking. They kind of warn you to make sure you're dark adapted. The cul-de-sac is just flooded with light, so it's not easy. I think if anybody was to try this in earnest, no, I was just kind of practicing, I would go to a darker place.
Mm-hmm. So you would not have to use averted vision, or you would still have to?
Well, I think you could try, but I'm just thinking that if you go to a darker place and your eyes are dark adapted, you'll be better.
Oh, yeah.
I think that would put another complication in for estimating the magnitude too, wouldn't it? To be
no, because it's uniform. I mean, you as an instrument, a recording instrument, is viewing it. That's why they call it differential, right?
Yeah.
You're viewing both the comparison and the target under the same conditions of.
Yes, yeah, you'd have to do that for sure.
Yeah, so environmental conditions like light, haze, as long as it's uniform, and then you as a human sensor, that's uniform, right? It's theoretically uniform. You're using the same sensor yourself and the same sky condition.
How do you look at your star chart without screwing up your dark adaptation?
I memorize it.
Okay.
Yeah, you look for your key pointers, right?
Yeah, I know the comp stars I'm going to use. I memorize them.
Yeah. Very, very, very dim flashlight.
Or you memorize them.
I have. It's quite dim that I can adjust right down to.
Yeah, so over to you, Randy.
Well, I am blown away, David, and I'm really excited by it. I think that it's just awesome. So when you go to the AAVSO website, you can plot. You can click on a little box that says all.
Yeah.
So I did RS OF and all, and this is what you get. And it's
so you have a wider span of time here.
Yeah, so we're going down to the early 1900s. Something funky is going on until 1933 or so. I can't really explain why it would be so,
they
so
knew
flat there.
They knew about it before that big spike in 1930, so I'm not quite sure why there's no values beforehand.
Yeah, but also why are they so darn flat there? I want to say this is the open circles are visible. So that's just, what David was doing, looking through the telescope through the eyepiece. And then I've also plotted in green the V band, which is, it's a pretty panchromatic filter. So
it's actually a green filter. And it's meant to simulate.
It's a green filter.
It's a green filter, yes.
Oh, no kidding.
And it's meant to simulate our vision, actually. That's why it's green. Panchromatic green.
Oh, boy. Okay. Well, because I see that the V and the Viz are the instrumented and the eye version of the same thing,
Yeah.
whereas the other bands don't match perfectly. Okay, so here we have it was wonderful Wilhelmina Fleming. I'm sure Margie
Yes.
talked about her, who discovered the first outburst.
Well, I should have mentioned that actually, but that's true.
1907 is just before the AAVSO started their recordings. 1933, 1945. Well, let me, I blew these all up to 2 years. Okay, so there's 1933. And it's interesting. It levels off a bit. That's called a plateau. And then it actually goes down to 12 and a half and then pushes its way up a bit. So each time it's going to be the same scale, vertical and horizontal.
Yeah,
this is all there was in 1946. So they didn't figure it out at the time, but in looking back, they realized that while RS Ophiuchus was behind the sun, there must have been one then.
Yes.
David, what were you going to say?
Yeah, you're right, and I didn't realize that. I didn't even think that that was a possibility, but you're quite correct. And the quiescence has been fairly predictable. They say the range is 12.5 at the quiet end.
So here we are in 58, and I want to point out there are some green points there. So they did use the photo multiplier or something. And it's when I did this exercise, I said, oh boy, there's something really interesting here. There's always this bump or this change in slope here about 2 months after the outburst. You don't see it so well because of the sun in 1968, but you see it really, really well in 85.
Yep.
And they were very lucky. They could have missed the beginning of it because of being too close to the sun. Here's the 2006, and you see it's very instrumented by then. Although, David, how do you actually get to put your visible light observations in? Because these people, the standard deviation is maybe half a magnitude.
Yeah, the thing to remember.
Less.
Yeah, the thing to remember, the standard deviation is relatively wide for visual, and the thing is, like, I wouldn't submit the ones that I did because I knew I made enough mistakes that I wouldn't kind of mess up the data, so I wouldn't do that. It takes a little bit of discipline to decide whether or not they seem legit or not, which is why we record the notes for the observing. So if there's an indication that you think that they're probably outliers, you don't submit them, right? So I know it really does take some clear skies and some dark skies to do this. I know that now, so I wouldn't. I mean, it's a lot easier when it's bright, when it's up in the 4, 5, 6 range.
Right.
As soon as it starts to creep down, especially in the suburbs, the binos aren't going to help you. It's just too much light pollution.
You can see people are reporting to the 10th of a magnitude.
Yeah.
There's scatter, but they're not. Nobody's giving to the 0.05. They're all doing it to the 0.1.
Yeah, they're not millimags. I mean, the thing to remember is those comparison stars are they're fairly spaced apart by comparison, right?
Yeah.
So you'll see like a 4.5, 4.6, 4.7. So you'll be there to the 10th. So if you were comparing stars, you could estimate how close something was. There were a couple of times when I looked at it and I thought, it looks just like this star. So I'll just use this value.
So what's pretty exciting for it was August 8th, and there are actually 4 measurements on the way up. But this guy named Geary in Ireland was the first. He's the one who gets the credit for seeing it. And it's really fun looking in, is it a cloudy skies? But there's a whole blog, and People
in
are all
cloudy nights.
congratulating him for finding it, and that's where he reported it. So we're talking about amateurs doing real astrophysics here, and that's very exciting for me.
You know, the psychological effect must be pretty hard too. If you're looking at something that others have reported a consistent number, consistent magnitude, and let's say you see it somewhat higher, you know, that pressure to say, well, there must be something wrong with the way I'm measuring it.
No, absolutely, David. You hit it on the nose there. And they do warn new observers, do not look at the light curve. Just report as you see it. Like, do the comparison, stay true to the technique.
Yeah. Okay, so let's talk about the astrophysics of this. So let's go right to the luminosity temperature curve. It's called, somebody help me. Again?
Russell Hertzsprung.
Russell Hertzsprung, yeah. So on the main sequence, these are the hydrogen burning stars. And when the hydrogen gets used up, then they turn into red giants as the helium then is needed. And if it's a sun relatively close to a sun mass, then what happens is they go pop, turn into a planetary nebula, and the thing that's left over in the middle, which doesn't have any fuel, becomes a white dwarf. So this is a graph of a binary system that's going to turn into a supernova, but it's actually just different masses, but it's exactly what's happening with RASC Ophiuchus. You've got a couple of stars, and we happen to know now that the first star is about 1.5 sun masses, and the second star is, about half a solar mass. When they're heavier, when they're more massive, then they evolve faster. So it turned into a red giant, and then it turned into a white dwarf, while the other part of the binary is still burning its hydrogen, but then it used up its hydrogen, turned into a red giant. Okay, so that's where this guy is. And they figure actually pretty soon, like in 100,000 years, RASC Ophiuchus could really be a type 1a supernova. So just hold your breath, guys.
I'll put it in my calendar.
Yeah.
Okay, so then during quiescence, so during the 15 to 25 years that nothing's happening, and you take a look at the H alpha line. So this is the hydrogen going to its main spectrum line. Then you get this really cool thing. It goes up, and then there's this notch, and then it goes up, and then it comes back down. And you see the units here are not in angstroms, they're in kilometers per second. So that's the Doppler shift of from what you're expecting. And the dashed line there is the speed, the radial velocity that this system is moving away from us. Okay, so it's centered not on 0, but on something like minus 30 kilometers per second. That's how fast the system's moving away from us. And when you take a look at the absorption frequency, then you get this curve going here. And that is at, what is it? 1.5 years, okay? And then when you take a look at this wider emission and take a look at its frequency, it's out of phase. Anyway, what they say is this is the cold partner, okay? So it is absorbing, it's got an atmosphere that is absorbing the light, and you have the hot partner, which is emitting light, and it's a lot more varied in speed. It's a more complicated system, Well, that's how they figure out that what you've got is you've got a red giant which is absorbing light in its atmosphere, and you've got this hot partner with a whole variety of speeds, which is emitting light and doing all the Kepler planet orbital law rules. Then they know what the ratio of masses between the red giant and the white dwarf are. And so they've got the mass. So 1.3 for the hot one, and the cold one is about 0.7 solar masses. And it turns out this is very, very hot for a white dwarf. White dwarfs tend to be smaller or less massive than the sun. This is very close to what you call the Chandrasekhar limit. And above that is where they turn supernova. And what's going on? Well, the red giant is big. It's a giant. And, between the two stars, there's a point where the gravity balances out between them. And so this curve here, the Roche lobe, is where the gravity balances out. And if the size of the companion is larger than the Roche lobe, then it starts bleeding its atmosphere in towards the little guy. Isn't that cool? And this happens a lot, apparently. So, so September 5th, 28 days after the outburst, right? The outburst the maximum was on August 9th. And turns out this guy, Steve Shore, is a astronomer at the University of Pisa, and he speaks with this funny New York accent. It's very strange thinking that he's living in Italy. And he is the big maven. Like, everybody is he's the variable star guy. And this first speaker, Francois Tessier, analyzed the spectra. But this is a really good still from the video. You see that they're only 1 AU apart. That's like the sun to Earth. We've got 2 stars. Imagine that we are a star next to the sun, and it's a red giant. Red giants, sometimes red giants, I think Betelgeuse is bigger than the Earth's orbit. Okay, so you can see how if a red giant is next to the sun, but only as far away as the Earth, it's going to be bleeding off mass. And it turns out that it is doing 10 to the minus 7 solar masses per year. Okay, so that is a 10 millionth. That's really fast. That means at that rate, in 10 million years, this star will disappear. Okay, and in astronomical terms, that's fast. So am I going to show you anything else from this slide? No, I think we'll go on. And these are amateurs who are doing the spectrographs. That's one of the things. So as well as the AAVSO, there's another organization of amateurs who like doing spectrographs. And so they're taking lots of spectrographs. This is in time, going from the outburst up to today. Well, the first 24 days. We're about 30 days in now, 35 days in. And so this is the quiescence, and you can see how it's evolving over time. And they're all excited about when you get helium showing up, and this thing in square brackets or here, those are called forbidden lines. Anyway, I'm not going to go into those, but it's all really very cleverly analyzed. That's what Steve Shore looks like. And you can see the difference between before, so that's in quiescence, and then with this great big shoulder, that's after the outburst, okay? And so here's kind of the model so you've got the shoulder. So you see there, the shoulder of the spectrum, this is always H alpha, but they look at every single line and they're trying to work it out. So with a great variety of speeds, so that means going away from us and going towards us, there is this emission, okay? But then there's also this very spiky emission, and that comes from the shock between the wind coming from the red giant and the wind coming from the white dwarf. So they bang together, and that's a very specific speed, and it's putting out a huge amount of H alpha radiation and a whole bunch of other, mostly hydrogen, helium, neon. And then you have absorption, and that's the light going through from the explosion and being absorbed within the atmosphere of the red giant.
Shocking.
Isn't that fantastic? Okay, the next thing, and I haven't really found out what this plateau is. And so, you know, I'll figure this another time, but it's called the wind phase. And then eventually you get these things called soft X-rays that are going to be on and then turn off. And that's going to be about 2 to 4 months in. In the red dots is 2006, and then this is the curve for 2021. And so in gray, you see what happened in 2006. In the red, you can see that the soft X-rays are just about to start. And it's amazing. Like it's not happening like clockwork. It can be only something like 15 years between some of these events, and it can be over 30, but it seems to be behaving itself the same each time. And what Steve Shore, he's very excited about this because it tells you not just about this sort of star, but he says this is the first time that they have characterized the atmosphere that the explosion is going through, and you can use the same sort of reasoning to talk about the supernova going through the interstellar medium. And he gives a whole bunch of examples where this is an amazing laboratory for figuring out how things work. He's a big thinker, and he's just so excited being able to work with amateurs, because that's what this workshop was for, the amateur community. And he likes doing things like he showed a video of a pizzeria oven and comparing it to what's happening there on the star. Is that where I finish? I think that's where I finish.
Very good.
So Randy, you didn't answer my question about the mechanism.
Okay, yeah, so it's hydrogen that it forms on the shell of the white dwarf, and when it gets to a high enough density, then you get a, is it called a there's a 3-letter acronym. Anyway, it's a thermonuclear reaction when the hydrogen gets to a high enough density and temperature to start nuclear fusion, but it's in the shell. It's not the core of the white dwarf is actually dead.
Yeah, it's a remnant star.
It's a remnant star, and it's just that it's a big mass, and that big mass is big enough that it can bring the hydrogen in. And when the hydrogen gets to it's the same thing with nuclear fusion that they do in laboratories on Earth. It's all about getting enough hydrogen at a temperature and density that the protons cannot fight their electrostatic repulsion. And
Well,
so
that'd be amazing to see in slow motion, a whole sphere of hydrogen just fusing, like, wow.
yeah, and then once it starts its runaway, that's what the R in TRG is. It's a runaway reaction because it creates heat, and that then makes the it's a positive feedback.
It's an exothermic reaction.
Yeah, thank you. And so you get more and more, and so that's why you go up a factor of 600. It was less than 24 hours. It increased in luminosity 600 times, and then it's going down 2 magnitudes every 5 or so days. David, what's a magnitude in terms of ratio?
It's in steps. I think it's in like 3 stages. Like it goes down probably relatively rapidly from the outburst, but it slows down. So now it's slowing down.
Yeah.
It's not going to change a lot until it reaches 12.5.
Great, thanks.
Yeah, I was saying to Randy how to me, like before I started looking at variable stars, the sky was kind of flat. Now it's 3-dimensional, which is great.
Interesting. Yeah. Well, thank you very much.
And a note from Jim Cliff of a Larry Niven story that describes one of these outbursts.
Oh, Beta Lyra, yes. Yeah, I observed that actually during the summer.
Very good. Okay, so next up is Nathan and Bryan.
We'll do it on mine.
Okay.
Oh, turn yours off.
We're getting an echo.
Computer's going here. All right. So we're just gonna find the screen. This is it. Do you want to start, Nathan?
Sure. Okay. Well, we got a screen share first. Oh yeah, we are. We are? Okay.
Yeah.
So yeah, this summer we decided to go on a road trip to Winnipeg. I would say that it was one of the highlights of the summer, but unfortunately it was the highlight of the summer. The only highlight, basically. Yeah, after a period of relative dormancy, we decided to go on a road trip to Winnipeg. This was for 2 reasons. First of all, because it was because air travel was, we weren't quite comfortable to be flying on planes yet, and second, because there are some pretty cool sights to see across Canada, including the night sky as well. We ended up taking some pretty cool sky pictures. That wasn't until later though. When we first arrived in Winnipeg, it was pretty smoky. I had originally been planning on borrowing a telescope from my fellow Winnipeg rascal, Mike Caracas. But unfortunately, after the smoke cleared, it started to rain. And it rained basically nonstop for, what was it, like a week?
Well, it wasn't nonstop. There was a few moments, but for
Yeah.
the most part, it was kind of gray. Yeah.
I remember the rain stopped for a bit during the thunderstorm. Anyway, so I ended up not borrowing the telescope, but yeah, I was planning on it. And while we were in Winnipeg, one night I just looked and saw the moon rising over the lake. We stayed at a cottage on Lake Winnipeg. Luckily, it's not on Lake Winnipeg. It's beside Lake Winnipeg. And it used to have one of the darkest skies that I had known. It's not the darkest sky I know now, thanks to another place we went to, but that was the place where we got pictures first. I managed to convince him to take his camera out on that clear night, and we got some pretty interesting pictures at the lake. We ended up seeing the Northern Lights. Now, my grandmother was asleep during that. We decided not to wake her, but the next day when she saw this picture, and I don't know if she really appreciates what long exposures do. So when she saw this picture, she was a little bit, I don't know, she kind of wished we'd woken her. Anyway, then we explained to her what long exposures do. they make things look a lot more impressive.
Keep going.
Sure. And this was the aurora with the moonrise. And it was still kind of smoky, so it gave the moon quite a red color.
Is that the Pleiades over the moon?
There you go. That's straight up.
Yeah, that was vertical, and compared to some of our others, it doesn't look quite as good now, but it was pretty good. The skies were pretty dark there. Is that the full picture?
Yeah, it's the full
Okay.
picture. Yeah.
This was a picture that we took of the Milky Way over the cottage that we stayed at. I think that was one of our best pictures, which I really like that one. Mhm.
So, oh, and that's the next day.
Right, that was the night after when the Northern Lights were still pretty good. And we thought that we were seeing a lunar halo as it was rising, but it turns out.
I think that it was just fog on my lens, and I think the camera hadn't acclimatized to the cooler weather. So, but I put this in this series just because I thought it was a pretty cool picture, but it really is just fog on the lens.
Mm-hmm. Did you keep the picture about the totally fogged?
No.
Oh, okay, because we ended up taking a totally fogged up picture.
So then this is a couple of pictures of the prairies and the sunflowers. And then we end up back at Lake Louise. On the way to Winnipeg, we hurried through the Rockies because of all the forest fires. And when we got to Lake Louise, there was a lot of haze, and then it started to rain. So we hardly saw the mountains. And but on the way back, we got to stop there and saw the mountains and saw the lake, and it was beautiful. I thought I'd put that one in. That was a nice picture. But Nathan had the idea that we should come back and see the Milky Way over top of Lake Louise. And do you want to tell me,
Sure,
talk about how we figured out when it was going to be directly across from the lake?
Yeah, so I wanted to figure out when the Milky Way would be right over the glacier. And it was pretty approximate. And I used Google Maps. And basically Google Maps has a tiny little compass at the top, which doesn't give exact directions, but it has 4 arrows, north, south, east, west, which I used to get an approximate measurement of the direction relative, the direction of the end of the lake where the glacier is relative to where we would be standing. And it was about southwest, almost exactly southwest. And then I used my night sky program, Starwalk 2, to find out when the Milky Way would be directly in the southwest. And I estimated it to be 10:30, and I was only off by 2 hours. And you can imagine when we're standing out there in like below freezing temperatures, when there was bears, like, okay, you want to talk about that?
I'll tell you. Well, so we showed up. What time was this? This one
This is
at?
probably 10:30.
This is okay.
Actually, it says 9:30, but that's
yeah.
because of a time change.
Right. So it was around 10:30, and this is Lake Louise at that time, and we basically, what I was really hoping for is to have the Milky Way coming down into that corner from that mountain and the glacier, and so we basically waited and waited and waited and waited and waited. And waited. By this point, it was getting pretty cold. And around this time, the Lake Louise Chateau security drove down right to where we were. And he was curious as to what we were doing. We explained that we were taking pictures of the night sky. And he kind of like wished us well. And he said he didn't like to kind of walk around at that time. He liked to prefer to drive because of animals. And I said, well, are there bears? He says, well, we haven't seen one in the past month. It's probably good if you have mace, which of course bear spray, which we didn't have. So that was on our mind, and it was definitely getting cold. And so finally, it got to. Is that the one?
No,
that I think that's.
I think there's one more.
That might be it. And then it finally got to the position that we wanted, and this is a picture. I've boosted some of the exposure and brightness on that, and I was pretty pleased with that picture.
I think that.
And then this is
yeah.
in landscape, kind of just positioning.
That took the title of the darkest skies we've seen,
Yeah.
which dethroned the lake that we took pictures at before.
So anyways, those are some of the cool pictures. I have to say I learned something. I really haven't done a lot of pictures. And David, I mean, obviously you're so much more skilled, and John McDonald has, presents these pictures. But I think, on the little screen of my camera, I thought, man, this is like magazine quality. And I realized probably to get the foreground in focus and the background in focus, you probably need to do the stacking. You probably need to take a picture of the foreground without the tracker, because when I brought it back onto the computer, I realized that foreground is a little bit blurry, or quite a bit blurry, but still impressive. So
yeah, or you just need to have like a lens like 2 meters wide to capture all that light instantly.
Nathan and Bryan, you guys are far too modest. These are excellent.
Oh, David, it's I can't. Oh, wait a sec. Sorry, I have it on mute. Sorry, I didn't hear what you said there.
Oh, I said you guys are far too modest. These are excellent.
Oh, thank you.
Yeah, you certainly got the focus of the stars pretty well bang on. So that's quite impressive. It's not easy, as you probably learned.
Yeah, and if you're not using any special techniques, even more kudos to you.
Well, thank you. Yeah. So I could just speak really briefly. I think I've talked about this to a few people. I took those pictures with this Pentax, and I got the camera just because I wanted a full frame camera, but Pentax has built-in stabilization in the body. You can buy lenses that have stabilizers in them, but Pentax has technology that stabilizes the camera in the body, and they use the same technology as an astrotracer, and so instead of putting this on a mount on the tripod, you just put this on the tripod itself, and the sensor in the back of the camera, using a GPS built into the camera, will move following the stars, and so I was able to, like, some of these pictures were for like 90 seconds. I think we pushed it to 2 minutes. You can see a little bit of trails sort of on just on the peripheries, but they're pretty sharp in the center. So
I've heard of this, Bryan, but I've never seen it in action. I guess I can say that I have now.
Yeah.
That's pretty darn clever, Bryan. Did you know that ahead of time?
I knew that it had this feature, but I mean, it's been like I didn't get into trying it in the first little while, and we've used it here a couple of times.
Oh, very good.
Yeah. So. Yeah. Anyways, thank you.
Am I imagining something? But is the reflection of the Milky Way in the lake?
There is.
A little bit, yeah.
It is. Oh, interesting, and it's moving. The stars have moved here.
Right.
Because it's tracking the actual sky, and the reflections would be moving in the opposite direction as it came down.
Your camera is very smart. You can tell the difference between a reflection and the real thing.
Good explanation there, Nathan.
Right.
All right. Well, thank you.
Well done.
Thank you.
Stop sharing.
Well, thank you so much. That was very neat. Dave, you wanted to tell us about a book, I believe.
Sure. I'll just share a quick picture, because the last time I was at Astro Cafe, I'd shown a picture of the Andromeda Galaxy, and someone asked me the question in the Astro Cafe, were we seeing stars in Andromeda? And I followed up on that by taking a larger telescope view. I gotta share my screen here. Is that coming through then?
Yep. Yes.
Yes, we see it.
So this is a close-up I took, I guess, of the Andromeda Galaxy to see if I could resolve the stars, if one could, with a backyard telescope. And if I zoom in, you can actually see those blue stars in the background are actually in Andromeda.
Yeah,
Sorry, that's of Andromeda Galaxy? All
That's
those.
Andromeda Galaxy, yeah.
Dave, this is so good, you must be cheating somehow.
You didn't know we had a 30-meter telescope that he's.
Yeah, right. It's hidden in the trees somewhere.
Yeah. but so I won't dwell on it. I don't want to.
It's beautiful.
I'll be talking more about that at the astrophotography SIG, but I did want to, because actually Brock, I don't think is Brock around?
Yep.
So Brock had a great idea. I got, I haven't actually used it yet, but a diffraction grid to put on the telescope, but I actually haven't used it yet. But Brock had a great idea, I thought, of how if we could create a slit blind in front of the grid, we could actually measure the spectrum with this diffraction grid of nebula. And it threw me back to a book I had read. Well, I had got in the 80s when it was newly published by Richard Feynman called QED. And I read this book every 5 years or so since, because to me it was a big introduction into quantum mechanics, and it really explains how light works, and it leads into a lot of the quantum mechanical effects that we see in space. It also explains how we were able to design things like telescopes and optics long before we understood that light was really a particle. And it really is a ground-shattering work in that he actually talks about quantum mechanics in a series of lectures to fine arts English graduate students at university. And that's where this lecture, so he actually explains it in a way that you don't require math. And so it's a great, even if you have math, it's a great introduction to this topic. And it goes, it talks about the limits of understanding this, and the biggest limit to QED and other quantum mechanics is that it is so absurd that it bothers you, and your initial reaction when you read it is that you don't believe it because it can't be, that nature can't behave that in such a bizarre manner. But it takes several readings, but each reading you come out of it with tremendous understanding of how light actually works and how it gets onto your camera, everywhere from how it travels through space, how gravity slows down clocks, so it's got some relativism in there, and acceleration slows down clocks. And I just wanted to while I was reading, I thought this would be a good book to recommend. So if that sort of interest has ever piqued your curiosity, this is a great starting point. It's not that big a book. It's an easy read. terms of actually reading it. And every time I read it, I learn something new that skipped past me somehow the last time I read it.
Yeah.
What year is it, David?
It was first published in 1984.
Yeah. So David, you are a certified physics nerd. I have the same book, and I got it to learn how reflection works. How does light reflect off of something? He actually does a pretty decent job of this, of explaining it, I thought. Now I'm going to put something out for everybody to buy, a teaser for them to buy the book. What did Richard Feynman do with the people that he really liked? Does anybody know?
He took him out for drinks.
Yes, you're right. And something else.
Drumming?
No. Oh, good choice. Good choice. No,
Gave them a book.
Pardon me?
Gave them a book.
No. First of all, like, you're right. He loved drumming, and he called all music is just drumming with notes, which I thought was an interesting way of putting it.
I have to bump in to say 1945. We lived in Cambridge, and I was 2 years old. And there's a letter in Richard's the collection of Richard Feynman's letters to his parents, where he says he arrived in Cambridge and he didn't know where to go, but a friend said, "Get hold of the Robineaus and they'll put you up for the night." And he describes a happy evening in my parents' house, including a mention of me as a cheerful 2-year-old.
Wow.
And my brother as a 7-year-old, not quite so cheerful, but talking to him about Menuhin's playing of a violin concerto of some sort. So I've got a connection.
Yeah,
Oh,
great. Awesomeness.
Okay, well, now that I have everyone's attention. Just a question, since that's a book on quantum physics, how do you even know what you're buying until you actually read it?
Well,
good try, Dave. Good try.
Yeah. Well, when you don't go to school for it, as I didn't, Richard Feynman is legendary, so I like the author. So you're getting it from the horse's mouth, if you would. He is infamous for being able to explain. I have his full physics lecture series that I've partially read over the years. But that and the fact that it was designed to introduce this topic to fine arts English students.
Oh no.
So that's who he wrote it for.
Non-believers.
Well,
not oh no at all. They're non-believers before they read, and the hope is they'll be believers when they do read.
Yeah, exactly.
Yeah.
You know, you can download all of those notes that you're talking about, Dave. They're online. They're readily available, and they're fabulous. There's a very good one he wrote on how do gyroscopes work.
Yeah. I'll have to look those up.
Yeah.
Anyways, I'll take enough of your time.
To quote our past president, going into the Feynman black hole will consume a huge amount of your time if you are a physics nerd.
Yeah. Good call, Dave. Good call. Good book.
Thanks.
Thank you so much. That put it a very interesting conversation there as well. John wanted to show something, but I don't see him here at the moment. So I think we'll end tonight with some shots from Edmonton, if Dave is ready to narrate.
Yeah. You can bring them up one at a time, and sure. They're mostly stories in addition to the photographs. The guys in Edmonton have found a new observing site at a place called the Stanger Hills, which is west of Edmonton and north of the town of Wabamun. So Alistair was out there a while back, and he just said that the sky is darker there than it is at our normal observing site at Blackfoot. Said he saw 12 meteors the night that they were there, a couple of draconids, some late Perseids, and a few odds and sods. So, but he just took a single frame, unprocessed shot with his 60 DA camera of our friend, the Milky Way. No processing. So that tells you how dark that site is.
Holy.
Quite amazing, isn't it?
60-second shot at ISO 6400.
Yeah.
So pretty amazing. And then Tom Owen has been fiddling around with filters, and he's taken this picture. And again, that's the Sol Nebula, IC 1848, I think it's called. So he's done a lot of processing on this. But again, this one's out at Pigeon Lake, which is south of Edmonton, and the skies there are Bortle 4.5, so another very good dark site that's within an hour and a half's drive of Edmonton. And then the last one is Denny Boucher, longtime observer up there, and he's got an unprocessed photo that's been cropped down of Pluto, where the arrow is pointing.
And there it is.
Yeah.
Easy to pick out.
Yeah.
I was thinking of what David was saying with trying to find things there, and this would probably would greatly be aided by taking a photograph.
Denny Boucher and Larry Wood are the two guys who are reported in Edmonton to have better eyes than average.
Isn't Pluto around Mag 16?
Yeah.
Well past visual. Well past.
Do they do planets as well? Sorry, that was a bad joke.
3 neat shots. Thank you very much, Dave, for
there you go.
sending those along.
Terrific.
Great. Is there anything else for this evening? So if not, just a reminder that we have a council meeting tomorrow evening, 7:30. So council members have received the Zoom link for that. As Randy said, if you have any comments about how we might be able to move forward with some things, certainly in trying to resume in-person activities at some point, please let us know.
Another announcement is on September 26th, Sunday, September 26th, noon to 4 p.m. Is the Fairfield Fall Fair. And a few people have volunteered. I will send out emails. They can provide AC powers, so we can do some, what do you call it, David? Electronically enhanced?
Assisted astronomy.
Assisted solar.
Is it going to be in the evening?
No, noon till 4, so solar.
That'll be solar stuff, I guess.
Yeah.
And guaranteed cleared that day, right?
Well, you have to ask Randy.
So one of the things there too is, and do we have a site plan for that yet, Randy?
Do we have a
site plan? Do they know where they want us to be? Because there's
no, but they'll provide
on the site there, so we do need to be probably as far away from the buildings as possible to still get some sun in the west.
It's going to be Porter Park, and I will talk to Terra Silva to say we need a sight line to the sun. So we do have to work that out.
Yeah, so we need to be further to, I guess that means basically further to the east, I guess, in the park.
I'm really glad you thought of that now.
Well, we've been there. And the later you are in the month, of course, the lower the sun is.
Right.
Randy, please give me a call because I've got a small scope with a solar filter. So if there's anything to see, we might be able to. But I'd be happy to be involved.
Very good. Okay.
Well, thank you everyone for an interesting evening. And
thank you, Chris.
See everyone next week. And some people will see tomorrow. And yeah, unless there's anything else, I guess we'll call it an evening. So thank you very much.
Good night.
Good night.
Thanks.